Somashekar Viswanath from UIUC, and the title is Experimental and Analytical Investigation of Concrete Subjected to Variable Amplitude Fatigue Loading. Somashekar?
Okay, very good morning, everyone. My name is Viswanath. I'm a PhD student in the Civil Engineering Department at the University of Illinois at Urbana-Champaign. My advisors are Professor Jim Lafay, who is also a professor here, and Professor Dan Kuchma, who is a professor at Tufts University. Topic of my presentation for today is experimental and analytical investigation of concrete subjected to variable amplitude fatigue loading. This is a very brief overview of my presentation for today. I'll give a very brief introduction and motivation. I'll follow it up with the overview of the experimental investigation program that we undertook. I'll show some preliminary results from 2 different fatigue test series, and then I'll wrap it up with some summary and future work. So getting started, when we look at the research that's already been conducted into concrete under fatigue loading, one thing that you can very clearly observe is that the primary focus has been on capacity. And when I say capacity, I'm referring to the number of cycles to failure, or N sub F, at a given stress state. So if the peak and valley stress levels are S min and S max, and if you think of fatigue loading continuously at this one stress state, the primary focus has been on determining the number of cycles to failure for that given stress rate. In spite of quite a few decades of research, there's no consensus on the use of any one equation as yet, which is one major drawback. Additionally, as I said, most of the research has focused on capacity. There's been limited focus on the behavior of concrete subjected to fatigue loading. On the other hand, when we look at the actual loads in the concrete structures, we are not going to see one stress rate. Rather, we are going to see a varying stress rate with either variable amplitude or variable sequence. This is referred to as variable amplitude fatigue loading. Some examples, for example, a bridge that is subjected to different vehicular traffic. So it's not going to be one stress rate, or a tower subjected to wind loads. The wind loads are going to vary with time, so it's not one stress rate, or an offshore structure subjected to wind and wave loads, etc. Which leads to the motivation for this research to estimate the capacity of a given structure when it is subjected to variable amplitude fatigue loading. As I said, variable amplitude essentially means there's a combination of stress rates and loading sequences. One example would be something as shown here, where you have some number of cycles in this first stress state. Let's say N1 in some stress state S1. Then you have N2 in S2, N3 in S3, N4 in S4, so on and so forth. So this problem is not something new. It's been existent. People have realized that this is a problem, and there are some existing methods for determining capacity in such a situation. Something that's most commonly referred to and used is something known as Palmgren-Minor hypothesis. The idea is quite simple. It's a linear damage accumulation hypothesis. So what it says is, if there were some N1 cycles in this first stress state, and if this first stress state had a failure number of cycles of NF1, then the total damage is the ratio of N1 to NF1. Similarly, you can find the total a damage in each of these stress rates, and the total damage would be the sum of the individual damages. If this total damage is less than 1, the structure is safe. If the total damage is greater than 1, then the structure has failed. Is the basic idea. This has been used with reasonable success in steel structures, but we should remember that in steel structures, we primarily see a linear elastic response, like the modulus of elasticity of a structure several years after its use is very similar to what it was initially. When we deal with concrete structures, that is definitely not the case. It's an inherently nonlinear material. So even in the very first cycle, the modulus of elasticity is not a constant. So now the question really becomes, can we apply a linear damage accumulation hypothesis such as the Palmgren-Minor for an inherently nonlinear material such as concrete? We anticipate that that's not going to be the case, which is the motivation for undertaking this experimental investigation. So this is an overview of the experimental investigation that was undertaken. As I said, we wish to do investigate the effect of variable amplitude loading, such as the one that I showed previously. And in order to do this, we needed to know what would be the failure number of cycles in each of these pins, NF1, NF2, NF3, NF4, etc. So to do that, before we did any variable amplitude fatigue loading, this meant that we had to do the regular fatigue loading test first. That we call it as the basic fatigue test series, which is essentially a single amplitude fatigue loading until failure, such as what is shown here. We have one peak stress level, one valley stress level. We're going to test it all the way up to failure. We're going to note down what is the number of cycles to failure or fatigue capacity in sub F. In addition, as I mentioned, one common drawback is there's been limited focus on behavior of concrete under fatigue loading. So we also wish to evaluate and document concrete behavior under fatigue loads. So in order to do these various tests, both the basic fatigue test series and the variable amplitude test series, we cast concrete cylinders in our lab. Normal strength concrete, roughly about 6 ksi or so. We cast 4-inch diameter, 8-inch height concrete cylinders. We used a 100 kip testing machine, or that's a 445 kilonewton capacity in SI units. And in this picture, you can see uh, a concrete specimen placed in the testing machine with the data acquisition system as well, which is an axial extensometer, which measured the strain readings, axial strain readings in this concrete cylinder as it was subjected to fatigue tests. Uh, Having prepared the specimens, the next step was to develop a test program for the basic fatigue test series. So we, in this table that I show here, the X marks the various combinations that were chosen. The combinations were chosen such that there was a meaningful range of peak and valley stress levels that we had considered, so that we could see the behavior and see if it was consistent across a meaningful range of peak and valley stress levels. Additionally, the combination selected was such that the expected failure number of cycles was in the practical range with regards to testing. And as I said previously, the loading, this was the basic fatigue test series. So it was a single stress state. The peak and valley stress levels were fixed. We decided to use a sinusoidal waveform between the peak and valley stress levels at a fixed loading frequency, typically 2 hertz or 3 hertz was the testing frequency that we used. And with these, so we conducted these various tests in the basic fatigue test series. We collected information about the fatigue capacity or the number of cycles to failure N sub F, and we documented the behavior of concrete through the fatigue loading process. So we look at some results from the basic fatigue test series first. As I said, we obtained the number of cycles to failure. We compared it with various models that were out there and compared them. We found that the model that worked best, as shown here, was the concrete fatigue life model given by Model Code 2010. As we can see here, it predicted fairly well the capacity, at least on average, when the number of cycles to failure was less than about 100,000. If the number of cycles was greater than 100,000, as seen in this bottom two plots, we see that the model was not so accurate. So for our variable amplitude test, we decided to choose combinations that were in this top plot only, essentially expected number of cycles less than 100,000. And as I said previously, another aspect that we documented and observed was the behavior. With regards to behavior, something that we observed was strain evolution behavior. So in this plot, what I'm showing is the evolution of peak strains through the fatigue loading process. In this plot, I'm showing the peak strain evolution for 3 different combinations. All of them had a peak stress level of 80% for the 3 different combinations, and in each combination, 4 tests were done. We see that peak stress evolutions were quite similar, although the combinations were quite different. So our conclusion was the peak strain evolutions are going to be similar when the peak stress levels were the same. On the other hand, in this bottom plot now, the peak stress levels increase from 75% to 80% to 85%, and we see that the peak strain evolution gradually increased as well. So we observed increasing peak strain evolution with increasing peak stress levels. Again, we had multiple tests in each of these combinations. Something else that was seen in all the tests that we did was this inverted S-shaped behavior for the peak strain evolutions. So in this initial portion, the rate of change of peak strains is quite severe. and then it eventually stabilizes in this middle portion where it is quite stable, and then towards the end it again begins to pick up. This was observed in all tests, which comes in handy in all our analysis. So having done the basic fatigue test series, our next step was to answer the very first question, which is, are variable amplitude tests necessary? Or another way of looking at it is, a linear damage accumulation hypothesis justified? To answer this question, we consider two combinations. Let's say with peak stress levels of 75% and 80%, and let's say that their failure number of cycles were just N75 and N80. So if we consider two loading scenarios. In the first one, we would load it at the stress level of 75%. We would load it up to 50% of its failure number of cycles, which is N75, after which we would switch to the 80% and then load it all the way up to failure. As we can see from the plot here, the peak strain levels are going to be roughly similar when we make this switch. As we can see from the plot here, the total number of cycles would be 50% for the 75% level and something greater than 50% for this 80% level. On the other hand, if we switched it up, if we did the 80% first, the total number of cycles to failure would be 50% at the 80% level, but then something lesser than 50% for the 75% level. So even with this really simple example, we could see that a linear damage accumulation hypothesis was not justified. And similar behavior is observed by other researchers as well in literature, where if a smaller level was applied first, followed by a larger level, the total number of cycles would be greater. On the other hand, if a greater was applied followed by a smaller stress level, the total number of cycles was lower. So this led us to believe that yes, variable amplitude testing was required. So we came up with a testing program. As a first step, we wanted to do a two-stage variable amplitude test, which is very similar to what I described previously, in which there would be one stress level first, and we would go up to 50% of its failure number of cycles, stop it, and then switch to the higher stress level as shown in this plot and go all the way up to failure. And as you can imagine, we can go both ways, either low stress level to high or high stress level to low. Similarly, we also wanted to do a three-stage variable amplitude where we would have three stress level variations. A very similar idea. The only change would be that in the first and the second stress levels, we would go up to 33% of the respective failure number of cycles. So that would look something like this. For the three stress level, we can imagine that they can be a monotonically increasing, in the sense low to medium to high or a high to medium to low stress level. But in addition, there's also this combination mixed stress level where we go from, say, low, high, medium, etc. These four various combinations. We decided to test these as well because these are more representative of the true variable amplitude loads that structures would see in their real life. So before we did anything, we had to decide what would be the failure number of cycles. So this is from the basic fatigue test series. I've already shown this plot. What can be observed is the on average, the model code predicted it well. But if you look at individual ones, for example, this one test, which is 80% and 10%, the failure number of cycles varied from 1,000 to 65,000 cycles. So now, what would we take as the NF value, and correspondingly, what would be 50%? For example, if we chose NF as this average value, which was roughly 10,000, 50% would be 5,000 cycles. But two of the tests would have already failed by then. And two of them, for them, it wouldn't have been 50%. This was a problem that we faced. In order to address this problem, we decided to go up to some number of cycles to see their behavior. This is for the case of 75% and 10%. We went up to 7,200 cycles, which is 1 hour of testing at a frequency of 2 Hertz. When we see this, what we observed was extremely different strain behaviors. So for these first two tests that we did, the number of if we looked at the peak strain behavior, we would anticipate that this is less than 50% complete. And then for these middle 4 tests, it was approximately 50% complete. And for this one test, it was definitely more than 50% complete. And we saw similar behaviors across different combinations. So this is for 75 and 10. And then similarly for all of them, we saw these different behavior, which has made our life quite difficult for now, which we are going to which is what we are trying to address currently. This leads to my last slide, which is just summary and conclusions. So from our basic fatigue test series, we gained an understanding about concrete capacity and behavior through the process. We proved that a linear damage accumulation hypothesis such as Palmgren minor wouldn't work. And we showed that variable amplitude tests are necessary. What we are trying to work on right now is to figure out what is the number of cycles that we would like to apply for a specific percentage completion, and to evaluate damage having known what is the number of cycles that we will apply. I would like to thank you all for your attention. If you have any questions, I'll be happy to answer them now.
Thank you, Somashekar, for the interesting talk.